In this video, I'll be talking about the sampling theorem and its implications. Sampling is when we convert a continuous time signal to the discrete time domain by taking its value at certain times. The sample points are spaced by what is known as the sample period, T sub s, or 1 over the sampling frequency or rate. This is done by multiplying the signal by an impulse train. As we know from the sifting property, each impulse will select a discrete value of x by scaling the impulse by the value of the function. This gives us discrete points which represent our signal in a computer, where we work with digital signals rather than analog ones. An impulse train remains an impulse train when going to the frequency domain, although the pulses will be spaced by omega sub s, or 2 pi over t. Instead of multiplying, we convolve the frequency domain signal with our pulse train, giving the convolution sum shown here. The result is multiple copies of our signal in frequency, which we can then feed into a low-pass filter to recover our original signal. The sampling theorem states that we must sample fast enough such that all the information in the signal is captured. This means that our sample frequency must be at least twice that of the highest frequency component of the signal. If this condition is not satisfied, then the shifted copies will overlap, and aliasing effectively kills the overlapping parts of the signal. This leads to issues when reconstructing our signal in continuous time. For example, we may get a choppy audio signal coming from our computer since all signals are continuous or analog in the real world.